Welcome to Oddly Real. I'm Nem Stefanovic. There are fundamental constants in nature that are the basis for our reality. These constants of nature include things like the speed of light, Planck's constant, and an elementary charge. These constants and a few more form the basis for the International System of Units, or SI units, that we as human beings use to quantify all aspects of nature. These constants each capture some aspect of nature. However, it may be surprising to know that there is actually nothing inherently special about the numbers associated with these constants. For example, there is no deep meaning behind the value 299,792,458 meters per second for the speed of light. This number is actually chosen by us. Yet, why does the speed of light, or all of the rest of the constants, have such elaborate numerical representations? Why not choose a simpler number for each constant? The reason for this is that human beings have been working with certain standard units for measurements, like meters or seconds, for a very long time. It became necessary to make the basis for those units much more rigorous and well-defined. So the values you see are actually selected to preserve those historic units of measurement, but with exact numerical values for the constants of nature without any uncertainty. These 7 different constants of nature, which are used to define 7 different SI units of measurement, form the basis for all other types of measurements within the universe. We start by defining the units of time, which we know as seconds. In order to define a second with great accuracy, we need a source that can time with high accuracy and reproducibility. The units of second was defined using the cesium-133 atom, which has 55 protons and 78 neutrons. Atoms in general have electrons that occupy distinct energy levels, which are quantized as required by the laws of quantum mechanics. Cesium-133 has some very similar lower energy levels, which we call ground state hyperfine levels. When an electron moves between two of these states, it emits a specific type of microwave radiation. The radiation oscillates at a specific frequency, meaning it produces a certain number of cycles per unit of time. We define 1 second as the time it takes for this radiation to make exactly 9,192,631,770 cycles. Why is the cesium-133 atom and its energy levels so important for defining a second? Why not pick some other apparatus like a swinging pendulum? The cesium-133 transition energy radiation has a very high frequency of oscillation, which makes it very granular. As a comparison, quartz crystals oscillate at frequencies from thousands to millions of megahertz, and early versions were created that would only lose 1 second of timekeeping for every 3 years or so. In contrast, a cesium atomic clock would lose about a second of timekeeping every 150 million years or more. In fact, modern experiments using strontium atoms have properties such that an atomic clock would only lose 1 second of time every 5 billion years or so. Another one of the most basic types of measurements we can make is that of length or distance. We define the speed of light in a vacuum to be c is equal to 299,792,458 meters per second. There is no deep insight into that number. It's entirely selected by us to produce our well-established unit of length, the meter. Thus, we can rearrange the constant c to get that 1 meter is exactly equal to the length that light travels in 1 divided by c of a second, or 3.3 nanoseconds. In order to define mass in units of kilograms, we start with the definition of the Planck constant, which we choose to be h equal to 6.62607,015 times 10 to the power of minus 34 kilograms meters squared per second. This constant is rooted in the basis of quantum mechanics, linking the frequency of light to energy and it is also found in the famous Heisenberg uncertainty principle, among many other places. We already defined the SI units for seconds and meters earlier, which are present in the base units of the Planck constant along with kilograms. Thus, we can work backwards from h to figure out kilograms using meters and seconds. We can rearrange our definition of Planck's constant h to derive an expression for kilograms as follows. Without doing the math, you can clearly see that m and s can be substituted for meters and seconds as required. So mass can be defined in terms of the foundational Planck constant. Next, we derive the SI units for electric current, or amperes. An electric current is made up of a net movement of charge through a cross-section. Individual charges are extremely small, so it's typically more practical to define a larger unit of measure composed of large numbers of charges, like amperes of current. We define the basic unit of an elementary charge, like a proton, equal to E equal to 1.602176634 times 10 to the power of minus 19 ampere seconds. Once again, we can rearrange this definition as follows. This means that 1 ampere of current is the flow of 1 divided by 1.6 and so on, which is equal to 6.24150907 times 10 to the power of 18 elementary charges per second. Temperature is determined using Boltzmann's constant. We define Boltzmann's constant, K, exactly equal to 1.380649 times 10 to the power of 23 in units of kilograms meters squared per K, where K is kelvins, the SI unit for temperature. Boltzmann's constant is significant in science since it is used to define the level of disorder within matter, also called entropy. The Boltzmann constant also provides a link between the average energy of motion of the molecules in matter to temperature. Much like we've seen with the SI units of mass and current, we can use the Boltzmann's constant along with our definitions of meter and kilogram to get a definition for temperature in kelvins. One of the more straightforward definitions is the mole, which represents the amount of substance in a standard SI unit. 1 mole is defined as 6.022140076 times 10 to the power of 23 elementary entities, such as atoms or molecules, for example. It's also called Avogadro's number. It's simply a large number that makes it convenient to work with very small particles like atoms. It provides a direct link between the atomic realm and our macroscopic world. Lastly, the SI unit for luminous intensity in a given direction is the candela, with symbol CD. We won't go into depth for this one, and we mention it just for completeness. It is derived from a constant called the luminous efficacy, which determines how well a light source produces light of a well-defined visible radiation. Like other SI units, we can use the constant kCD along with our definitions of meter, second, and kilogram to obtain the candela. Extraordinarily, these 7 different SI units, based on 7 different constants in nature, form the basis for all of our measurements in the universe. There's an interesting note about the measurements of time in seconds and length in meters. Although we're familiar with time and length being separate and distinct types of measurements, technically speaking, they're actually related to each other. They are 2 different ways to measure the same thing, the dimensions within our 4-dimensional spacetime. Time can be measured in units of meters, and length can be measured in units of seconds. It is only for historical reasons and convenience, before the discovery of relativity and the 4-dimensional connection between space and time, that people have measured time and space separately. In fact, they are related to each other through the constant speed of light, where length in meters equals c, the speed of light, times s, seconds. For example, 1 meter of time is equivalent to 3.3 nanoseconds, which is the time it takes for light to travel across 1 meter of distance. Technically, we only need 6 basis SI units. But what about other phenomena in nature? For example, the SI units of force, which is a push or a pull on an object, is defined in units of newtons. Or how about energy, which has units of joules? How do these and many other types of measurements fit into the SI system? And what's their relationship to these SI base units? All other measurements, like these examples, are composites of the SI base units. For example, let's look at the SI unit for force, which is the newton. A force is a mass times an acceleration. Mass is the base SI unit of kilogram. Acceleration is expressed as meters per second per second. Thus, the newton is actually a composite unit that can be rewritten as 1 newton of force equals 1 kilogram meter per second squared. Additionally, let's look at the SI unit for energy, which is the joule. We can define useful work in units of joules as a force applied over a displacement. Work, W, equals force, F, times displacement, D. We know that force is composed of the base SI units of kilograms meters per second squared. The displacement is measured in meters. So 1 joule is equivalent to kilograms meters squared per second squared. It's pretty amazing that all of the phenomena in nature can be distilled into 7 constants that produce 7 related units of measurement. I hope you enjoyed this episode, and remember, oddly real, really interesting.